Data structures. I have tried to record this multiple times with various technical difficulties. It's getting painful. This chapter describes some things you've already learned about already in more detail, and adds some new things as well. This list data type has some more methods. Here are all of them. List.append takes one argument and it adds that item to the end of the list. And it is equivalent to simply taking a slice of a given list, which begins at the index whose number is equal to the number returned by calling the length function on the list, and goes to the end. And what this means, because Python is zero indexed, and so the first index will always be index 0, and the final index in any sequence of any length the index number is going to be equal to the length of the list minus 1. That looking for the index that is equal to the length of that list, taking a slice that starts there and goes to the end, as indicated by the colon on the right-hand side, means that you are looking for the empty index just beyond all of the indices that actually have data stored in them. And you are selecting that and sort of temporarily creating like an empty sublist at the end of the pre-existing list, and immediately updating the value of that empty sublist to contain this on the right-hand side. And by so doing, you will append to the end of that list this thing on the right-hand side. Thankfully, we don't have to do that because the .append method exists. There is list.extend, which takes an iterable as a list, or as an argument, and it is essentially like list.append, but it extends the list by appending all the items from the iterable passed in. And so it is equivalent to the exact same code here, except updating the value of that empty sublist with an iterable. List.insert takes two arguments, and it will insert an item at a given position. The first argument being the index of the element before which to insert. So a.insert 0, x would insert at the very front of the list, because it's just before what is at index 0. And a.insert length of a, x is completely equivalent to .append, as we, for the reasons aforementioned. List.remove, which takes a single argument, will remove the first item from the list whose value is equal to x. And it will raise a value error if there is no such item, and if there's duplicates, it will ignore them. It will just take the first one out. List.pop, which takes a single argument, removes, which is the index number, removes the item at the given position in the list and returns it simultaneously. So it will not be in that list after you call this, but you will get that value returned to you and pipe it into other things if needed. If no index is specified, a.pop removes and returns the last item in the list. It raises an index error if the list is empty or the index is outside the list range. List.clear will remove all of the items from the list, clear them out. And that's equivalent to using delete on a slice of the list which contains the entirety of the list. I think this is a little bit funny that this exists, but that's what that is. It's like saying, I'd like a slice of that cake. How big? Can you just hand me the whole thing? And I will call that a slice. List.index, which takes this, and these are optional arguments, return a 0-based index in the list of the first item whose value is equal to x. Will raise a value error if there is no such item. The optional arguments start and end are interpreted as in the slice notation and are used to limit the search to a particular subsequence of the list. The returned index is computed relative to the beginning of the full sequence rather than the start argument. List.count returns the number of times x appears in the list. Takes one argument, counts it. List.sort sort the items of the list in place, and the arguments can be used for sort customization, and they'll go into more detail about that later. List.reverse, I think you can guess. List.copy returns a shallow copy of the list, and that's, again, equivalent to taking a slice of the list which contains the entire list. That you've got sort of a temporary kind of copy of that in a sense, just like how doing this like sort of makes an empty sublist, but doesn't make actually a permanent copy. Alright, here's some examples. Say we got this list of fruits: orange, apple, pear, banana, kiwi, apple, banana. We call the count method with apple passed in as an argument, and it tells us how many times that string appears. When we ask about a tangerine, since the list doesn't contain it, we get a 0. Ask for the index at which we can find the string banana, and because again Python is 0 indexed, 0, 1, 2, 3. Fourth position in the list, called index 3. I'm sure that there is some practical reason for that. I'm too new to know why, though, and it seems ridiculous because of my ignorance. Fruits.index banana, 4. By adding this second optional argument, it will search the sequence for this string passed in as the first argument, starting at index number second argument. So 0, 1, 2, 3, 4. It can only look beyond that for the banana, and that's where it finds it, index 6. Fruits.reverse won't show us anything, just using it. We'd have to call the list afterward to see the effects, which are reversing the list. Fruits.append with grape passed in. Now we'd have to call the list again to see it, but grape's on the end. Same with fruits.sort. It sorts it lexicographically like a dictionary. Fruits.pop will return to us pear because it removes and returns simultaneously. Right now, if we called fruits again, we wanted to see fruits again after we do this, pear would no longer appear. It only returns it and shows us that value once. Now you might have noticed that methods like insert, remove, or sort that only modify the list have no return value printed. They return the default none. This is a design principle for all mutable data structures in Python. Remember, mutable, changeable. Another thing you might notice is that not all data can be sorted or compared. For instance, a list containing the value none, the string hello, and the integer 10, it won't sort at all because all three of these things are fundamentally distinct types that have no way of actually comparing and being ordered into a hierarchy. Integers can't be compared to strings, and none can't be compared to anything else. Also, there are some types that don't have a defined ordering relation. For example, 3 plus 4j, which is a complex number, right, or imaginary number. It's like I in mathematics. 3 plus 4j is less than 5 plus 7j isn't a valid comparison because there's this magic going on in there. Now, using lists as stacks. The list methods make it very easy to use a list as a stack. In a stack, think about stacks. Just in physical space, you're a human being. You stack stuff one on top of the other. And the last thing that you place on the top of the stack is the first one that you can retrieve, and that's what's meant here. The last element added is the first element retrieved. In other words, last in, first out, LIFO. To add an item to the top of the stack, use append, because in a stack, the end is the top. To retrieve an item from the top of the stack, use pop without an explicit index, because remember, pop without an argument passed in just goes to the last thing. For example, say we made a list that we called appropriately stack. We set 3, 4, and 5 to be the values inside this list. If we use the .append method and pass in 6, and then we use the .append method again and pass in 7, and then we call stack, then we will see that 6 and 7 have been appended to the end, or the top of the stack. We call the .pop method without arguments. 7 That's removed, but returned to us once. Now we ask for stack again, we see 7 is gone. We pop 6, we pop 5, we got 3 and 4 left, that's it. Come on, we can jive. Using lists as queues. It is also possible to use a list as a queue, and my fellow Americans, if in case you didn't know, a queue is like a line, wait in line. That's a queue, where the first element added is the first element retrieved. Or if you ever worked in a kitchen, FIFO. However, lists are not efficient for this purpose. While appends and pops from the end of list are fast, doing inserts or pops from the beginning of a list is slow, because all of the other elements have to be shifted by 1. If you want to put something into index 0 at the beginning of the list, then whatever is currently in there must be moved over, and then whatever is currently in index 1 must be moved over to make room for that, etc. on down the line. Which gets cumbersome at a certain point. To implement a queue, use collections.dq. That's how I'm going to pronounce this, even though it kind of looks like dec. I'm assuming that it's DQ because it's, a foil to queue, which was designed to have fast appends and pops from both ends. And this is how this works. So first you'd import this DQ module from collections. Q equals DQ, and in parentheses we've got the square brackets with the contents of the list inside, that you're making this list into a DQ by phrasing it like this. And then if we want to append another string, and then we append a second string, now Terry and Graham are in our list at the end. We can't see it yet. But if we then use the pop left, this is only when we're dealing with DQs that we can specify pop left, and it'll work just like .pop normally does on the right-hand side of a list. We'll do the same thing to the far left item. And so we're returning this first value, Eric, and removing it from the list. Then we call it again. We'll return what is now the first value, John. And after all of this hubbub, we call queue again. We just ask to take a look at it, and we see, as I mentioned earlier, this DQ and the parenthetical statement is now like built into this thing. It is a DQ now. And so it will show us that again whenever we call for the list, whenever we ask the interpreter for the list. List comprehensions provide a concise way to create lists. Common applications are to make new lists where each element is the result of some operations applied to each member of another sequence or iterable, or to create a subsequence of those elements that satisfy a certain condition. For example, assume we want to create a list of squares, of square numbers. We could define an empty list, squares, and then iterate through the numbers 0 through 9 for x in range 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For each number in that range, we will stop and carry out these instructions, because that's how a for loop works. At 0, we will try to append onto the end of this empty list the result of squaring x, the number that the spot in the iterable that we're at in the for loop. So the first round we've got 0 and it's nothing. We add 0. The second round we're at 1, 1 squared is 1, so we add 1 to our empty list. Third round, 2 squared is 4, and so it's 4 that we add to the list. So on from 0 to 9, range 10. And after this for loop is executed, if we then ask for this list squares again, we will see that it has a series of square numbers, the squares of the numbers 0 through 9. Now note that this creates or overwrites a variable named x that still exists after the loop completes. We can calculate the list of squares without any side effects using this fancy little wordage. Use a lambda function which at x does this, squares x in this range, we can map the results of this to this range. That this map function takes in two arguments. This is the thing that it will map. This is what it will be mapping it onto. That it will go through, it'll iterate through this range, and at each spot in that range, it will map the result of this onto that. And all of that is wrapped up in the list function. So a list will be made of the output of calling the map function on, or calling the map function with the arguments this lambda function mapped onto this range. Or equivalently, we could just do a list comprehension, and in our definition of the list, in our creation of it, built in, we can add all of the shit that it needs to do to create itself. That squares is a list that does this thing for each spot in this range. It's the exact same meaning as all of this, just said very concisely and in one line using a list comprehension. And as they say, it's more concise and readable. I agree, tutorial. A list comprehension consists of brackets containing an expression followed by a for clause, then 0 or more for or if clauses. The result will be a new list resulting from evaluating the expression in the context of the for and if clauses which follow it. For example, this list comp combines the elements of two lists if they are not equal. We got a tuple with x and y for x in a list containing the integers 1, 2, and 3, for y in a list containing the integers 3, 1, 4, if this condition is met, x is not equal to y. And this will produce this list in one line. And we can break this down by looking at what it would be equivalent to not using a list comprehension. Like, let's say we just make an empty list called combs for some reason. Oh, combination, that's why. and we make two for loops, one nested in the other. The first for loop is for x in 1, 2, 3, so at each item in this list. For each item in this list, we will execute this for loop, the second for loop, for y in 3, 1, 4. And so we will iterate through this, and for each item in this list, we will iterate through each item in this list. And as we're doing that, we're checking at every single step of the way if x is not equal to y. And if it isn't, if this is the case at any one of these steps when we check it, then we will use the .append method to append to our empty list combs a tuple containing the values of x and y at that point in the iteration. So, this ultimately produces all of these because, let me just make sure that you're tracking this. Let me just do it step by step. For x in 1, 2, 3, this will start here, and then we will be checking 1 against 3, we will check 1 against 1, we will check 1 against 4, and then we move on to the next step in this for loop, 2. And at 2, we will check if 2 is equal to 3, if 2 is equal to 1, if 2 is equal to 4, one after the other. Then finally 3, and we will check if 3 is equal to 3, 3 is equal to 1, 3 is equal to 4. And every time throughout that process that we find that the x value, the item in this list that we're iterating over, is not equal to the item in this list, then we append those values at that point in a tuple to this list. So since 1 is not equal to 3, we add a tuple saying 1, 3. Since 1 is equal to 1, the second step of this loop, it's not added. 1 is not equal to 4, so that's our second tuple added. And all of this can be expressed in one single line. Create a tuple containing values of x and y for x in this list, for y in this list, if x is not equal to y. Note how the order of the for and if statements is the same in both of these snippets. If the expression is a tuple, e.g. the x, y in the previous example, it must be parenthesized. So say we've got a list called vec. It contains these values, -4, -2, 0, 2, and 4. Say we wanted to create a new list that had all of those exact values except each one doubled. We could just make a list comprehension where we describe the operation that we wish to perform on each item in the list vec. We will square x for each x in vec. And this will produce all of its own, this list containing 4 doubled, or -4 doubled, -2 doubled, 0 doubled, 2 doubled, and 4 doubled. Now, if we wanted to filter the list to exclude negative numbers, then we could say x for x in vec if this condition is met, if x is greater than or equal to 0. Only then and only then will we add x for x in vec to our new list. We can apply a function to all of the elements in the list. So here's, again, is the here's just a simple arithmetical operation. Here's a function, but it's both the same order. This is the thing that we're trying to do for each item in list. In this case, we're calling the absolute value function on x. So whenever it reaches an item in list vec that is negative, it will return the absolute value of that, and so we ultimately have just a list of positive integers in the new list. We can call a method on each element. So say we've got a list of fruits again, and if we say weapon.strip for weapon in fresh fruit, because for some reason they just remember this is the same as X or Jim Jam or item or whatever. This is just the sort of temporary placeholder name that you come up with. You can call it anything. And in this case, because they're nerds, they try to make it funny. And this is what you're trying to do for each item in list. You're trying to apply the strip method. And so, as you see, these strings all have a bunch of extra, random white space and stuff on either end, and the dot strip method removes all of that automatically, and so returns a list without all of these extra spaces around the strings. We could create a list of 2 tuples, and did we talk about this? A 2 tuple is just a tuple that contains 2 values, and I think it's a real missed opportunity that they didn't call them couple tuples. That's just my opinion. So here is a tuple, the kind of tuple that we wish to create for each item in range 6, 0 through 5. That we will create a tuple containing the value x and the value of x squared. So at 0, we've got a tuple 0, 0, 1, 1, 1. Finally, 2 is interesting. We've got the value of x and the value of x squared. And we do that through the numbers from 0 to 5. If the tuple must be parenthesized, otherwise an error is raised. So say we try to do the exact same thing, but we just left these variables just naked and cold out in the open air. Then they haven't been defined by the hug of the tuple as tuples. And the interpreter will return a syntax error asking us if we forgot parentheses around the comprehension target. We can also flatten a list using a list comp with 2 for. And to flatten a list means, say, if you've got a list like this, which is each item is itself a list containing multiple values. To flatten such a list would be to create a list that contains just those values all in one, all in the open air within that list, And so this is going to do something similar to what we did earlier, that it'll iterate through, start here and iterate through all of this, then move on here and iterate through all of this. Sort of like that, because it's using two for loops, that num for element in vec for num in element. We'll just take 1, 2, 3, 4, 5, 6, 7, 8, 9, and step by step add those to this new list that we're defining, and so we will ultimately end up with basically a copy of this, except everything's been freed up. Now, list comprehensions can contain complex expressions and nested functions. So, for instance, say we imported the Pi module from the math library in order to be able to use certain things like round and pi and whatnot. So I mean, here, this is what we're trying to do for each item in this list or this range or whatever. That's in range 1 to 6, starting at 1, going up to 5. At each step in that iteration, we'll create a tuple containing the values of pi and the index number, that is pi rounded to I. Pass those in as arguments to the round function, which will round down this number to this number decimal places. So if this was pi, 2, then this is what that would output, right? But since it's pi, I, the variable defined here in this for loop, that is going to update at each step of the way. I is going to increase by 1 each iteration. And that's why we're getting 3.1, followed by 3.14, followed by 3.142, etc. And we're going to take the output of passing these arguments in to this function by passing all of that in as the argument to the string function, which will return the output of all of this as a string instead of floats or whatever. Nested list comprehensions. The initial expression in a list comprehension can be any arbitrary expression, including another list comprehension. Consider the following example of a 3x4 matrix implemented as a list of 3 lists of length 4. Since a matrix is, a grid defined by its columns and its rows, you can make matrices, and there's apparently a lot of different situations where people do this for various functions. You can make a matrix and define a matrix by just having a series of lists, a list of lists. Each one of these sublists is a row, and stacked atop each other like this, you can see how they have columns as well. I can't highlight that in that way. So the following list comprehension will transpose the rows and the columns, and so it's changing the x-axis to the y and vice versa. By comprehending, it's a list comprehension, which comprehends a list comprehension. That row given number in for loop. Row is your given number in the for loop. For row in matrix, you will be doing this. Row at I at row, row at I. Actually not. Just a second. Just like with our other list comprehensions, it starts with the thing that you're trying to do, and then describes to what you're doing it. So for I in range 4, that is 0, 1, 2, 3, at each step along the way through this for loop defined here, you will carry out this nested list comprehension, which for every row in matrix carries out this operation. And this will result in, see how 1, 5, 9 is a column initially. This will make 159 into the first sublist. So if we displayed it again like this, then we would see that the rows and columns have been transposed. As we saw in the previous section, the inner list comprehension is evaluated in the context of the for that follows it. So this example is equivalent to if we just made an empty list called transposed, define the for loop for I in range 4, and then put these instructions underneath it indented, meaning that for each step in this for loop, these instructions are executed. We will use a .append method on this empty list transposed, and to the empty list transposed, we will append the result of using this for each row in matrix, which in turn is the same as making an empty list called transposed, and for I in range 4, making another empty list called transposed row, and for each row in matrix append to this list transposed row the result of this, and once that's completed, append to transposed the entirety of transposed row. Asking the interpreter after all of this nonsense once more for our formerly empty list transposed returns the desired transposed matrix. In the real world, you should prefer built-in functions to complex flow statements. I don't think anybody would have to be told that. It's pretty obvious. Why? I can see why I would prefer that. The zip function would do a great job for this use case. Think of a zipper. A zipper is two sequences. There's little individual teeth, and they come together one at a time, and take the two sequences and mesh them together. Sort of like that, except if I did that correctly. So the zip function would do a great job for this use case. You take the star matrix, it's like the unpacked matrix, pass that into zip function, and make a list out of it with the list function. And look at that. In just one little line, you do the exact same thing as all this bullshit. Okay. The del statement. There is a way to remove an item from a list given its index instead of its value. The del statement, which henceforth I'll call delete. This differs from the pop method, which returns a value. The delete statement can also be used to remove slices from a list or to clear the entire list, which we did earlier by assignment of an empty list to the slice. For example, say we've got a list A, which equals all of these numbers. If we delete A at index 0, and then ask to see A once more, we see it is unchanged except for the removal of this integer here at index 0, which was formerly at index 0. Now 1 is at index 0. Now if we wanted to use the delete statement on a slice of list A, which begins at 2 and goes up to but not including 4, so that's index 2 and index 3, then ask for A, then let's see, this is index 0, index 1, here's index 2 and index 3. Since we've used the delete statement, on a slice of the list from 2 to 4, and ask for A again, we see 333 and 333 have been removed. Or we can just take the whole ass cake slice that contains the entire list, use the delete statement, ask for A, what do we got? An empty list. Delete can also be used to delete entire variables. Pretty self-explanatory stuff there, folks. I think you got that one. Referencing the name A hereafter is an error, at least until another value is assigned to it. We'll find other uses for delete later. Feels ominous. Tuples and sequences. We saw that lists and strings have many common properties, such as indexing and slicing operations. There are two examples of sequence data types. See sequence types, list, tuple, range. Since Python is an evolving language, other sequence data types may be added. There is also another standard sequence data type, the tuple. A tuple consists of a number of values separated by commas. For instance, say if we created a variable t and wanted to set it to the values this integer, comma, space, another integer, comma, space, and a string. If we then ask to see what was at index 0 of t, it will return this first value that we listed on the right-hand side here when creating and defining it. And if we ask to see t in its entirety, then we would see the entire series of values wrapped in that soft hug of parentheses. Tuples may be nested. You can have tuples, the items of which are themselves tuples. So say we made a new variable, u, and we set it equal to the value of t, which we previously defined, comma, space, and a tuple. A parenthetical statement with a series of values inside separated by commas. If we then ask to see u, then we will have an overarching tuple containing within it two items. The first being this tuple we previously defined, t, and the second being the tuple actually written out here. Now, tuples are immutable. Hugs are forever. If we try to, for instance, update the value of t at index 0 to anything else, in this case 88,888, we will get a type error telling us that tuple object does not support item assignment because it's immutable. Once that's been set, that's just how it's going to be. But they can contain objects which themselves are mutable inside themselves. Kind of odd. But for instance, say we had a tuple that had two items in it, both of which were lists. Lists being mutable objects themselves, we can do things to lists out on their own in the wild. But, I mean, wait a second. Now I'm actually not clear. I don't know if they remain mutable, can you still do shit to the lists once they're at a part of a tuple? Or is it just saying that despite it being a mutable object out on its own, you are still allowed to add them to a tuple, where they become immutable because they have become part of a tuple? If somebody would explain that, that'd be cool. As you see, on output, tuples are always enclosed in parentheses, so that nested tuples are interpreted correctly. They may be input with or without surrounding parentheses, although often, as we saw earlier in the first example, we didn't put, that's scrolled way too high. Fool. We didn't put parentheses around these when we defined it, but because it's a series of values separated by commas, that's what it's going to create, a tuple. And anytime we call it subsequently, we will see the parentheses. Bada bing, bada boom. Although often parentheses are necessary anyway, if the tuple is part of a larger expression. It is not possible to assign to the individual items of a tuple. However, it is possible to create tuples which contain mutable objects, such as lists. Though tuples may seem similar to lists, they are often used in different situations and for different purposes, and as has already been said, tuples are immutable and usually contain a heterogeneous sequence of elements that are accessed via unpacking, which we still haven't gotten to, but we will soon, or indexing, or even by attribute in the case of named tuples. Lists are mutable, and their elements are usually homogeneous and are accessed by iterating over the list. A special problem is the construction of tuples containing 0 or 1 items. The syntax has some extra quirks to accommodate these, because normally, again, a tuple is a series of values separated by commas, so what do you do with just 0 or 1? Empty tuples are constructed by an empty pair of parentheses, just like making an empty list. A tuple with 1 item is constructed by a value with a comma. It is not sufficient to enclose a single value in parentheses. For whatever reason, the commas are the key in a tuple. Ugly, but effective. It's like the opposite of me. For example, an empty tuple that we named empty can be defined this way. We can define another variable called singleton, set it equal to the value of the string all on its lonesome. As long as it's followed by this comma, then it will make a tuple. Otherwise, without the comma, singleton would just become the string hello. That's what it would, Now, if we call the length function on our empty tuple, we get 0. We call the length function on our singleton tuple, we get 1. We take a look at the singleton tuple, and we see it is wrapped in the warm embrace of parentheses, but its singular value retains the comma as if it's got friends. The statement t equals integer, comma, space, integer, comma, space, string is an example of tuple packing. The values 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, and hello are packed together in a tuple. The reverse operation is also possible. It is called unpacking. So say we told the interpreter x, y, z equals t. Well, we'd be doing the reverse. This is called, appropriately enough, sequence unpacking, and works for any sequence on the right-hand side. Sequence unpacking requires that there are as many variables on the left side of the equals sign as there are elements in the sequence. Everything's got to have a place for everything. Note that multiple assignment is really just a combination of tuple packing and sequence unpacking. Noted. Sets. Python also includes a data type for sets. A set is an unordered collection with no duplicate elements. Basic uses include membership testing and eliminating duplicate entries, because you can pass in a bunch of data that has a bunch of duplicates in it, and if you make a set out of it, then that set will just automatically remove all the duplicates that you've got in that data. Set objects also support mathematical operations like union, intersection, difference, and symmetric difference. And I think we'll go over this more, but just briefly, so that to help improve retention. Union. All of these mathematical operations can be pictured as Venn diagrams. Take two items, and they've got a little bit of an overlap in the middle. So union is everything that's in this one, everything that's in this one, and everything that's in the middle in both of them. Intersection is only the stuff that is found in the intersection, in the overlap. So nothing that's unique to A, nothing that's unique to B, only the items which are present in both A and B. Difference will depend on whether it's the difference A minus B or B minus A, but it's like subtraction. And symmetric difference, which is in the Venn diagram, it is everything but the intersection at the center. So if where the two circles overlap are not included, only the things on either side, what is unique to A and what is unique to B, but not what is shared between them. And we'll go over that more. If that didn't stick, it's fine. It's just it'll help it stick by going over multiple times. Curly braces or the set function can be used to create sets. And the set function is important because if you're trying to create an empty set, just using empty curly braces, you'll create an empty dictionary, not a set. So you have to use the set function to create an empty set. Now here is a brief demonstration. We have set the value of the variable basket equal to this set, as indicated by the curly braces or brackets, and the fact that these aren't pairs. These aren't key value pairs, which are what dictionaries consist of. These are just individual items, unordered. This is when we're creating this set, we passed in all of these strings, and as you can see, there's lots of duplicates in here. There's 2 apples, there's 2 oranges, and Python will be forgiving and allow us to create this set. It won't freak out when we give it these duplicates, but it will just kick all of them out. It'll just make all of them vanish automatically. And if we call, say, the print function on this set, print basket, what it will show us is what we gave it minus all of the duplicates. We can ask, is orange in your basket? And we'll get true. Is crabgrass in your basket? Ain't no crabgrass in my basket, so you get false. Here's demonstrating set operations on unique letters from two words. So, say we set a variable A and a variable B. We set the value of this variable A to equal the output of passing in the string abracadabra to the set function. We set the value of the variable B equal to the output of passing in the string alakazam to the set function. And since strings, strings work a lot like lists and everything else. I mean, they're sequences too. It's every individual letter in a string has its own index, just like items in a list. And so passing in abracadabra or any other string is like giving it a series of individual letters. And so now, once we've made the set out of this string abracadabra, if we then ask to see that set, you can see it's removed all the duplicates. It's no longer readable as the word abracadabra, but might be useful for something. Now here's the difference. Letters in A but not in B will produce R, D, and B. This character is called the pipe. You would read it aloud, this phrase here, as A or B. And those are the letters in A or in B or in both. That's union, because that's everything. A ampersand B, which you'd read A and B, letters in both A and B. That's intersections, only the stuff in the middle overlap of the Venn diagram. This character is called a caret, C-A-R-E-T. I just learned that. And that indicates symmetric difference. And this will give us the letters that are in A or B, but not in both. So all of the letters which are unique to both of those, but none that are shared between them, that's symmetric difference. Now, similarly to list comprehensions, set comprehensions are also supported. So there's clever ways to, in a single line, create a set, the logic used to create it. That is very much just like a list comprehension. You can say X for X in abracadabra if X not in ABC. We'll compare these with these operations. And what it'll give us? The result of that, and without duplicates, right? Now, dictionaries. Finally here. Dictionaries are sometimes found in other languages as associative memories or associative arrays, because that's their key function, is that you've got a fixed things, keys, that you can associate mutable things values to. Unlike sequences, which are indexed by a range of numbers, dictionaries are indexed by keys, which can be any immutable type. Strings and numbers can always be keys. Tuples can be used as keys if they contain only strings, numbers, or tuples. In other words, if a tuple consists entirely of immutable objects, then it can also be used. But if it contains a single mutable object, either directly or indirectly, it can't be used as a key, because the whole point of the key is that it's fixed, that it points to a fixed spot in a computer memory. You can't use lists as keys, since lists can be modified in place using index assignments, slice assignments, or methods like append and extend. So it is best to think of a dictionary as a set of key::value pairs. I said that colon aloud, but because that's part of the syntax, is that the key is on the left-hand side, it's followed by a colon and a space, and then you put the value or values to which they associate. The values that associate with it, you know what I mean. With the requirement that the keys are unique within a single dictionary. It's a little bit like an apartment building every apartment has a number, and whoever's living there, it doesn't matter, that apartment number remains fixed, and that's important for the directory to function, right? You can have one person living there and multiple people that can come and go. You can still find them by looking up the key, by looking up the apartment number and going to that apartment number. You can't find them where they're positioned in the apartment building with their personal name. You find their apartment number. That's the fixed thing. So a pair of braces, as we mentioned earlier, with nothing inside, creates an empty dictionary. And placing a comma-separated list of key-value pairs within the braces adds initial key-value pairs to the dictionary. This is also the way dictionaries are written on output. And you can update a dictionary and add key-value pairs and whatnot, just that you can pass some in when you first create it too. The main operations on a dictionary are storing a value with some key and extracting the value given the key. It is also possible to delete a key-value pair with a delete statement. If you store using a key that is already in use, the old value associated with that key is forgotten. It's gentrified. Somebody moves in and they kick out the old person, but the key remains the same, the apartment number remains the same. It is an error to extract a value using a non-existent key. You can't look up in the directory or go visit the person at the apartment that doesn't exist. Performing list with the dictionary passed in on a dictionary returns a list of all the keys used in the dictionary, in the same way that the directory at the apartment building just has the apartment numbers, and that's, or in a map to find them or whatever. But this metaphor is getting a little bit strained, but it doesn't contain the name of every person that has ever lived there, right? It'll tell you where the apartment numbers are. And it returns it in insertion order. So, but if you want it sorted, you can just use the sorted function again. To check whether a single key is in the dictionary, use the in keyword. So here's a small example using a dictionary. So say we created a dictionary that we're calling tell by creating a variable called tell and setting the value of that variable equal to these key value pairs inside curly braces. Remember this, the first is the key, then the colon, and the value or values associated to it. In this case, we've got two keys, Jack and Sape, the values 4098 and the values 4139 attached to them. Now, if we look for this, if we look for a key Guido and set it equal to a value 4127, that will create Guido with the value 4127 attached to the end. And if we look for the pre-existing key in it, tell at Jack, it will return the value associated with that key. If we use a delete statement on this dictionary at the key Sape, then as we can see here, when we later take another look at the dictionary, not only is Sape removed, but the value associated with it is removed. In the same way that if you demolish one of the apartments, you will also remove all of the people that lived in that single apartment. If we pass the entire dictionary into the list function, it will return a list of the keys alone, because the keys are the meat of the dictionary. And if we pass the dictionary into the sorted function, we would again be returned just the keys, but sorted lexicographically like a dictionary. Alright, there was someone creeping around outside my bedroom window. It turns out there was no danger, but I did stop for a second and look. Now, say we ask about a key in tell. We just say key in dictionary will return the Boolean true or false. It will just check, is this key in this dictionary? Is this key not in this dictionary? In this case, since there is a key, Jack, then it returns false. Now, the dict constructor builds dictionaries directly from sequences of key-value pairs. I'm sorry, God. Sorry, Mom. So, say we pass in, we've got these tuples, string, integer, string, integer, string, integer, separated by commas, and we arrange these three tuples, themselves separated by commas, inside square brackets, and then that whole mess we pass in as an argument to the dict constructor. This will produce a dictionary in which the first item in each of these tuples is made a fixed immutable key, and the second items are made the associative values. Now it's got curly brackets or slash or braces, and each they're separated by colons, the key value pairs. In addition, dict comprehensions can be used to create dictionaries from arbitrary key and value expressions. So for instance, actually, just a second. Okay, I just had to think about how to word that for a second, but in this dict comprehension, it's saying make this kind of key value pair for each item in this tuple. Make x into a key and make x squared into a value for each x in tuple. So this for loop will iterate through this, and at 2 we'll make a key equal to 2 and a value equal to 2 squared, so on and so forth. Produce a dictionary with the following key value pairs: 2, 4, 4, 16, 6, 36. When the keys are simple strings, it is sometimes easier to specify pairs using keyword arguments that really clarify and drive it home. So instead of putting the string SAPE and the string Guido and the string Jack, you make each of these keyword arguments, and they will become key words. That this will automatically be interpreted as meaning that this is a value associated with this being a key. And so that's what you'll get back is like, and you see these are strings still. You just didn't need the quotes around them because up here because you're making them keyword arguments. It returns the exact same thing. Looping techniques. When looping through dictionaries, the key and corresponding value can be retrieved at the same time using the items method. So items returns key value pairs as individual items. Like saying, those Jimmy and Jam have been going out for a while. I guess they're kind of an item now. They become a single unit using the items method. So say we have a dictionary called Knights, which contains the key value pairs Galahad and the Pure, and Robin and the Brave. And for key comma value in Knights.items, print key comma value, we will be extracting pairs as individual units, and for each pair, printing that pair. And since it's a new print statement, each iteration of the for loop, it'll be on 2 different lines in this case because there's 2 key value pairs. And we'll print Galahad the Pure and Robin the Brave. I don't remember Robin the Brave, the stories of King Arthur's court, but whatever. When looping through a sequence, the position index and corresponding value can be retrieved at the same time using the enumerate function. for IV in enumerate with this list tic-tac-toe passed in as argument, print I, comma v will print the index followed by that value at that index, and then again, just like this, it'll be each on a new line because it's a separate print statement iterated, or that's executed each time this loop goes another round. You know what I'm saying? 0 tick, new line, 1 tick, new line, 2 toe will be the output. To loop over 2 or more sequences at the same time, the entries can be paired with the zip function. So say we have a list with 3 strings in it that we call questions. We have a second list with 3 strings in it that are the corresponding answers. For question, comma, answer, in the result of calling the zip function with each of these lists, one after the other, passing as arguments, print what is your 0. It is 1 dot format Q, comma, A. Have we done the dot format? I don't think we've reached the dot format, but this will, whenever it's printed, whenever this runs, everything that is inside these curly braces inside the string here will be replaced, will be formatted with the value of Q and A at 0 and 1 respectively at that point in the loop. So in this case, it would print what is your 0 is name in the first step of this loop, and 1 is Lancelot. Name and Lancelot. What is your quest? It is the Holy Grail. What is your favorite color? It is blue. Zip. To loop over a sequence in reverse, first specify the sequence in a forward direction and then call the reversed function. So, here we pass into the range function the arguments 1, 10, and 2. And remember, the range function can be called with 1 argument, 2 arguments, 3 arguments, slightly different each time. If it's 3 arguments, the first number is where the range begins, inclusive. The second number is where the range ends, exclusive. So in this case, it's 1 through 9. And the third argument defines the increment at which it will step through that range. So it will go every 2 numbers. That's the range. That's the sequence in a forward direction. And if we pass all of that, the output of this, in as an argument to the reversed function, then we get the reverse of that, right? So from 9 to 1 in increments of 2. And for I in the reversed of the range 1, 10, 2, or each item in this defined reversed sequence, print that item will get us starting with 9, then 2 down 7, 2 down 5, 2 down 3, 2 down 1. And even though it's reversed, of course, like, don't get confused that, because range, it's still, this is only the number that's going to be exclusive. So even though it's reversed, it doesn't make, and this is like the end, that's still inclusive. Probably nobody was actually confused about that, and I might have just confused you more. To loop over a sequence in sorted order, use the sorted function, which returns a new sorted list while leaving the source unaltered. So say we have a list containing a sequence of strings, and for I in the result of passing in that list to the sorted function, print I will get us apple, apple, banana, orange, orange, and pear, sorted lexicographically like a dictionary. Using set on a sequence eliminates duplicate elements. So you might want to just make a set out of a series of stuff if you just want a quick way to get rid of all duplicates and only have unique items. And so the use of sorted in combination with set over a sequence is an idiomatic way to loop over unique elements of the sequence in sorted order. So say we have that same fruit basket with the same weird duplicates in it. If for each fruit in the result of passing that list into the set function as argument, and the result of passing the output of that in as argument to the sorted function. For each f in that, print the fruit. You get apple, banana, orange, pear. Because it has ordered it lexicographically and removed all duplicates. It is sometimes tempting to change a list while you are looping over it. We're only human. Sometimes we give in to the temptations like changing a list while we're looping over it. It's a huge scandal in the Catholic Church. However, it is often simpler and safer to create a new list instead. Don't give in. Say we import math in order to allow us to do some of the other things in here. It's not really that important, but I mean, to this point. But say we made a list called raw_data, and it is equal to the series of floats and a couple of these weird attempts to turn the string NaN into a float. And we also create an empty list filtered _data by simply setting the value of a variable equal to 2 square brackets with nothing inside. Creates an empty list, right? Now for each value in this first list, raw data, if said value is not equal to the result of passing that value in as argument to the isNaN method from math, then append that said value to our empty list filtered data. So it will iterate through every item in this list. It will check if it is not NaN. And God help me, I don't have any idea what that means. But I mean, you can tell from context. I don't know what a NaN is, but it's saying this is not a NaN. This obviously is a NaN. So if it's not a NaN, it gets appended to our new list filtered data, so that if we call filtered data after this, we just have these floats and not this weird shit. More on conditions. The conditions used in while and if statements can contain any operators, not just comparisons. The comparison operators in and not in are membership tests that determine whether a value is in or not in a container. The operators is and is not compare whether two objects are really the same object. Is this that? Is this not that? All comparison operators have the same priority, which is lower than that of all numerical operators. So if it's you're in a situation where you've got more than one kinds of operators going on, keep in mind that this is will be executed lower or ordered lower in the hierarchy. Comparisons can be chained and performed one after the other in the order that they're written. For example, A less than B equals C will test first whether A is less than B, and moreover B equals C. Now, or I guess no, it's simultaneous, isn't it? Not one after the other. Comparisons may be combined using the Boolean operators and or, and the outcome of a comparison or of any other Boolean expression may be negated with not. These have lower priorities than comparison operators. Between them, not has the highest priority because what is more firm and clear than a not, and or is the lowest because what's weaker than a wiffle waffle, okay? I hope that's a helpful mnemonic. It's fun to do. So that A and not B or C is equivalent to if we put first not B, separated that in its own parenthetical statement, within A and not B, its own parenthetical statement, separated from or C. It's equivalent. As always, parentheses can be used to express the desired composition, and if you really want to be sure about something, it is nice, you'd probably just use the parentheses to be absolutely certain that you've cordoned everything off correctly. The Boolean operators and or are so-called short-circuit operators. Their arguments are evaluated from left to right, and evaluation stops as soon as the outcome is determined. For example, if A and C are true, but B is false, A and B and C doesn't even evaluate the expression C, because it doesn't have to. This can only return true if all the values are true, and the second that one is found false, just like falsifying a universal claim, you don't need a whole bunch of particular pieces of particular evidence. As long as you see one that disproves the claim, then it's done. You don't have to continue checking. Since B, it finds as false, it just doesn't even bother checking C, because it won't change anything. It will remain false. When used as a general value and not as a Boolean, the return value of a short-circuit operator is the last evaluated argument. It is possible to assign the result of a comparison or other Boolean expression to a variable directly. So for example, say we had variable 1, variable 2, variable 3, and we set them all equal simultaneously to string 1, string 2, and string 3 respectively. Then we created a variable non_null, and we set the value of this variable equal to the result of asking string 1 or string 2 or string 3, which I called earlier variable 1, variable 2, variable 3. It's a little confusing. Non-null, the value of this variable will become the result of this, which is, in this case, Trondheim, because it is the first one that it reaches that isn't nothing. Okay? That is not null. And it will stop. It won't even evaluate Hammer Dance because it doesn't need to. Note that in Python, unlike C, assignment inside expressions must be done explicitly with the walrus operator. I almost forgot about this. Shit. Oh my god, I miss my laptop so bad. This fucking thing doesn't work in so many ways. I can't even like zoom in without it all. It's like trying to move an image in Microsoft Word. Holy Lord God Almighty, where even am I? Well, that really sucked the joy out of finding the walrus operator, folks. But the walrus operator is called the walrus operator. Have I not already seen this? Okay, yeah. Wait. Must be done explicitly with the walrus operator. And I'm just going to have to ask you to just lean in real close to your screen and take a look at that. Like this. Do it like this. Because it's called the walrus operator because it looks like a walrus. It's got two little eyes and two big tusks. Because it's a colon followed by an equal sign. And I'm just so glad. But yeah, you have to use that to assign values to variables inside expressions, because otherwise it would get real confusing with a single equal sign and double equal sign. Just there's one clear, obviously different way to do that in those contexts. This avoids a common class of problems encountered in C programs, typing equal in an expression when equal was intended. Comparing sequences and other types. A sequence objects typically may be compared to other objects with the same sequence type. The comparison uses lexicographical ordering. First, the first two items are compared, and if they differ, this determines the outcome of the comparisons, or of the comparison. If they are equal, the next two items are compared, and so on until either sequence is exhausted. So just like two words in the dictionary that start with the same several letters, or like Jeff and Jeffrey, if you spell it the weird way and you spell Jeffrey Jeff, then Jeffrey will come after Jeff. J will be compared equal, E is compared equal, F compared equal, F compared equal. Finally, you reach one where it's not equal, and that determines the ordering. If two items to be compared are themselves sequences of the same type, the lexicographical comparison is carried out recursively. If all items of two sequences compare equal, the sequences are considered equal. If one sequence is an initial subsequence of the other, the shorter sequence will be the smaller, lesser one. Now, I'm even actually a little bit confused there because. Well, no, I mean, I'm not. No, because that's what I was saying with the Jeff and Jeffrey, is that because Jeff is an initial subsequence of Jeffrey, if you spell Jeffrey wrong, I mean. And so Jeff will be in position that is higher in a sense, but lower in another. Like, because it would be like 3 in the list would be Jeff, and 4 in the list would be Jeffrey. And so in a sense, it's higher in the list, right? I'm not 100% sure that that's right. But nobody's watching this anyway. It's just important that it looks like I've made these, you know. Okay, lexicographical ordering for strings uses the Unicode code point number to order individual characters. Some examples of comparisons between sequences of the same type. So we've got a tuple and a tuple. This one is less than this one because the first item is equal, the second item is equal, but the third item we see is less than the third item in here, so this is less than that. You have 2 lists, which repeat the exact same process. Here, ABC is less than C, is less than Pascal, is less than Python. And that's just like this would be ordered in the dictionary, right? And 1, 2, 3, 4, it's actually less than 1, 2, 4. Because even though the third element in this one is higher than the third element in this one has 4 elements. Even though there is this 4th element that is higher, actually, rather, it would be the way to put it, that because it reached a higher one at the third point, then that sets this already as higher. So we got a tuple 1, 2, and a tuple that is 1, 2, and -1. Kind of the same, the inverse of that. And here we've got integers 1, 2, and 3, and floats 1.0, 2.0, and 3.0. And even though these are 2 different things, you know, that their value is considered equal, because it would be insane if it wasn't. And here we've got 2 tuples that each of which in their third spot and index 2 contain another tuple that itself contains 2 values. You might just take a look at that and consider that if this doesn't make sense yet. Note that comparing objects of different types with the chevrons less than or greater than is legal, provided that the objects have appropriate comparison methods. For example, mixed numeric types are compared according to their numeric value. So, as we just saw, 0, the integer, equals 0.0, the float, etc. Otherwise, rather than providing an arbitrary ordering, the interpreter will raise a type error exception. It won't just come up with a way to decide that oranges are better than 6. It will just say, I can't order these. Footnotes is telling me something about other languages, and I don't give a shit. This one is enough.